So we're looking at the definition, formal definition of limits again. And I just kind of wanted to review what we had touched on yesterday and do a couple more examples. And then I am hoping to get to continuity, what it means to be continuous at some value x equals a, and being able to show that mathematically. So right here we have the formal definition. So let's just kind of go through that again. I hope you guys can see this. Let me blow it up a little bit. Let f of x be a function defined on an interval that contains x equals a, except possibly at x equals a. Then we say, and we've used this notation before, right, this limit as x is approaching a of f of x equals L, if for every epsilon greater than 0, then there's some delta greater than 0 that the following holds. So our function of x minus L, this is less than epsilon. Well, f of x, remember, recalls, let's just kind of talk about this while we're going through. This would be our f of a, if it exists there. So it's that y value that we're getting closer and closer here. Minus L, well, this is a L, sorry. So this is, but if we're looking at f of x minus L, so this is our whole function f of x. This has to be less than epsilon. So we're choosing some epsilon that's positive. The better, the smaller it is, the most infinitesimally small it is, the better and precise we are. And so this is going to happen whenever we have some delta that's bigger than 0 and the absolute value of x minus a is less than delta. Okay. So basically, it's kind of like a game. In here, you're going to say, I'm going to choose some epsilon in here. And if I choose that some epsilon in here, I want you to be able to tell me what this delta is going to be in here so that you are for sure, when you choose some x value in here, you're for sure to be inside of this yellow region. Okay. So let's look at an example. So here you're actually given the graph of f of x, and it wants us to find delta such that for all x, that 0 is less than absolute value of x minus c is less than delta. Then we know that our function f of x minus L, the absolute value of that, is less than epsilon. Okay. So in here, it's shown us where we're going to approach. It told us that f of x is equal to x squared. Our c value, which we're getting closer and closer to, is equal to 2. The limit that it's approaching, we can see is on the graph is 4. And epsilon is 2. So that distance above and below what we're approaching is 2. So if we kind of go backwards from our y value and go to our where we hit the graph to see what x value gets us there, we can see on the left of what we're trying to approach is square root of 2. So our left bound on here is root 2. And then we're going to have some value here, which is 2. And we have here root 6. So we need to figure out what this distance is in here. And it might be the same and it might not. And so recall to find distance. So we want to find the distance of c minus delta on the left. So if we do that, we would have 2 minus root 2. If you plug that in the calculator, let's just get an estimate of what that is. So 2 minus square root of 2. Where did the square root go? Gosh, my eyesight. Oh, I'm square root of 2. There it is approximately 0.586. So now let's look at it on the other side. So if I want to find the distance between C and this value in here, this value for delta is going to be, in this case, it's going to be C minus delta. Our C value in here is 2 minus delta, or actually, it's not delta, that's root 6. This is going to give us an approximate value, plugging in the calculator. So root 6 minus 2 is another way to do that, so we don't have to take the absolute value. We get approximately 0.449. Okay, so we need to choose delta to be the smaller length of those two distances, so that we know for sure that we would fall in this range here. And so you're always going to look at, if it's not symmetrical about the value x equals c, then we're going to choose delta to be the smaller of the two, to be the smaller distance. And so in this case, we're going to choose delta, and we'll just write it like this, to be root 6 minus 2. I believe in the homework I wanted the exact value. But if we wanted to round it, we could say, well, delta then is approximately, we're rounding it to the thousandths, 0.449. So technically, if we really want to be exact, we could say round it up. Delta is approximately 0.45. Let's look at one more example. So looking at one more problem from this section, similar to something that you'll see on the homework. The problem says, for the given function f of x, the number L, C, and epsilon greater than 0, find an open interval about C on which the inequality, the absolute value of f of x minus L, is less than epsilon holds. Then then give a value of delta greater than 0 such that for all values x satisfying that 0 is less than the absolute value of x minus c is less than delta, the inequality holds for this. Okay, so let's write this out. I don't know why it's not writing though. Okay, so we're looking at this. We have our f of x value. We're given what L is, we're given what C is, and we're given what the epsilon is. And so recall, we want this f of x minus L to be less than epsilon. So let's just fill in the pieces. So we have the square root of 24 minus x minus our L value, so minus 1. We want this to be, the absolute value of that to be less than epsilon. And it gave us what we want to stay within, so 0.1. And we're trying to figure out what delta we need so that this will always hold true. That will be 0.1 away from our L value, which in this case is 1. Okay, so let's first start by rewriting this. 0 point without the absolute value. So to drop the absolute value of an inequality, that is a less than, you kind of sandwich it in between the negative and the positive. So negative 0.1 is less than the square root of 24 minus x, and then minus 1 outside that absolute value, or outside that radical, is less than 0.1. So recall yesterday, our whole goal was to figure out what delta was to get this f of x minus L, that absolute value, this piece to look like this absolute value of x minus c. And once we did that, we could choose what this was over here. Okay, so looking at what that would be in our case, well, our c value here is 23. Okay, so let's start here. Let's go back to our inequality and work with that. So let's isolate this square root, and let's add 1 on both sides. So doing that, we have negative 0.1 plus 1. This is 0.9 is less than the square root of 24 minus x is less than 1.1. So we want to get this to have an x. We don't want that square root. We want to get rid of that square root. So let's square both sides of the equation. Squaring is not going to change the inequalities. So 0.9 times 0.9, I kind of ignore the decimal for a second. 9 times 9 I know is 81. I need to move now the decimal over 2 spots. So this is going to be 0.81 is less than, well, we squared the radical so we could get what was underneath, 24 minus x, is less than 1.1 quantity squared. Well, let's just think of it as 11 times 11 first. And that I know is 121. And I'd have to move my decimal place over twice. So that would be 1.21. Might have been off a little bit on this. So let's, for a second on this problem. So let's add 24 on both sides of the equation. Let's try to isolate that x. And so if we add 24 to both sides of this equation, we get 24.81 is less than negative x. Actually, I don't want to add 24, do I? How do I get rid of that 24 there? I'd have to subtract it. Okay, so 24 minus 0.81. So this would be negative 23.19 is less than negative x, which is less than, so I have 1.1, no, 1.21 minus 24. This gives me negative 22.79. So this is, we want to be x and not negative x. So we can just multiply everything through by a negative 1. The only thing is that we have to be careful because remember when you're dealing with inequalities and you multiply or divide by a negative, that swaps, that changes the sign. So this is now going to be a greater than in here. So doing that, we get positive 23.19 is greater than x is now greater than this 22.79. Okay, so we rewrite this. So this is 22.79 is less than x. I like the smaller number on the left going to the larger number is less than x, which is less than 23.19. Okay, so recall that we were having our x value was at 24. Sorry, was at 23. That was what we're trying to find the limit about. And so if we were looking at this and we had some value here of 23 on the x-axis, and over here we have, and I'm going to enlarge it, let's say 23.19. And we had this 22.79. We're trying to figure out what that distance is. So we need to figure out, okay, how far is it from 22.79 to get up to 23? And so if we look at that, 23 minus 22.79, that distance is 0.21. If we look at the distance in the other place, right here, that distance from 23 to 23.19 is 0.19. So that distance, the surrounding the x equals c, or 23 right here, is not the same on the left and the right. So if they're not the same value, you have to choose the smaller one. So delta is going to be the smaller of the two. Because if we choose the smaller of the two, then we know for sure that we would get in between that f of x minus L. We would stay within that epsilon, that distance. And so, did it say? So we found our delta. I know it wanted us to, let me go back to what it wanted us, find an open interval about C on the inequality. So we found delta, and we're going to choose delta to equal 0.19. So if I'm looking at that interval around C, right, I would have C minus delta, comma C plus delta. Or in our case, this would be C is 23 minus 0.19 and 23 plus 0.19. So the values that we would be in between and staying, well, that would be 22.81, comma 23.019. So if we chose any x value within these values, we would know for sure that we would stay within the y value of f of x minus L.